So for these first 6 problems, we're just trying to expand them. So we see log base 3 of 4 times x, and we write that as 2 separate logarithms being added together. So log base 3 of 4 plus log base 3 of x. The second one, natural log, we can rewrite as natural log of 15 plus natural log of x. And just a reminder, natural log is the exact same thing as like log base e, but we write it as ln instead. That's all that is. Okay, so it's just a different base. Number 3 is going to be natural log of 12 minus natural log of 5. And of all these problems so far, none of them simplify easily, so I'm just kind of skipping over that part. Problem number 4 is a log base 10 because there's no base written there. So we can rewrite this as log of 5x minus log of 6. There's just one issue here. We actually have this 5 times x, so we can actually expand it a little bit more. We write it as log of 5 plus log of x minus log of 6. That would be the complete expansion for this problem here. All right. For problem 5, I really like this problem in particular because we can look at the old method that we were talking about when you have log base 5 of 1/5 equals question mark. You could rewrite that and think about it as 5 to the question mark equals 1/5. And then you say, oh, well, I remember Mr. Street said I can flip that over and it becomes a negative exponent. And then I have that 1/5. So it really turns out that the exponent is just a negative 1 up there. So we know that this result is negative 1. And now if we fast forward to what we learned yesterday and what we're working on today, we can write this as log base 5 of 1 minus log base 5 of 5. That's how we separate this division problem. And we might remember from when we did the number lines last week, log base 5 of 1, anything base of something of 1 is just 0. And anything like log base 5 of 5, base number of the same number, is 1. So this is 0 minus 1, negative 1. So we get that same exact result. That's how these properties work. All right, breaks it up and gives us the exact same result that we would have had if we just thought about it as switching the whole thing around. Okay, so I think that's a pretty cool example to show us what's happening here. All right, last problem, log base 3 of 7xy. So we write that as log base 3 of 7 plus log base 3 of x plus log base 3 of y. Just separate every individual component. Don't leave something still combined. That's really the key for these particular problems. All right, any questions on that warm-up before we move on today? No questions? All right, so what we're gonna do now today is we're gonna talk about a new property of logarithms, but first let's talk about the other two again. First one, we said when you have multiplication of two numbers inside of a single logarithm, you can write it as addition of two separate logarithms. The second one we talked about yesterday, log base b of m minus log base b of n. That was when you had division of a single logarithm of numbers inside of a single logarithm. You could write a subtraction of two separate logarithms. And the last one, which I'm going to explain right now, has this log base b of m to the n power. And what we can do is we can take that n and we can drop it off out in front of the logarithm and rewrite it as n times log base b of m. This one's called the power property. And again, I don't expect you guys to have the names of the properties memorized, but we do need to know how to use them. And when we have this power property, it's going to help us solve exponential equations, and that's what we're going to be looking at today, moving towards solving. But first, let's take a look at like how to prove this power property. We're going to look at two separate logarithms here. One of them, log of x squared equals y. The other one, we're going to use like generic letters, log base b of m to the n power. And we're going to look at them side by side. So the first step here, when we're looking at this first problem, is we will convert to exponential form. And we're going to do that in both problems actually, but convert to exponential form. All right, we should hopefully be pretty good at that by now. This is log base 10, even though it doesn't have a base shown there. So this is going to become 10 to the y power equals x squared. And the next thing I want to do is I'm trying to get x by itself. I want to square root both sides, because I want to get rid of that 2. But instead of actually doing the square root, what I'm going to do is I'm going to raise both sides to the 1/2 power, because that's the same thing as square rooting both sides. And while I'm doing this on the left side, I'm going to do the exact same thing on the right side of the equation as well. The first thing I did was I changed the form, so it's b to the x equals m to the n. And instead of square rooting both sides, I'm going to go nth root of both sides. So b to the x equals m to the n, 1 over n. And when I square root both sides, this really becomes 10 to the y over 2 power equals x to the 2 over 2 power. And the other side becomes b to the x over n power equals m to the n over n power. And so what I've really got here is I've got 10 to the y over 2 equals x, because the 2 divided by 2 is just 1. So now, when I've got this rewritten like this, and I've got x solved for, basically, I'm just going to erase this right now, because x is solved for. I'm going to convert back to logarithmic form. And what's going to happen when we convert it back, we're going to see a slightly different problem here. So base 10 becomes base 10, so log base 10, again, of x equals y over 2. But before we had y equals, so I want to get back to that y equals again. I'm going to multiply both sides by 2. I'm not going to write the base 10 anymore, but I get 2 times log base x, or log base 10 of x equals y. And if I did the same thing on the other side, convert it back to logarithmic form, log of b of m equals x over n, and then I'm going to multiply both sides by n, and I'm going to get equals x. Sorry, I ran out of room there. N log base b of m equals x. There we go. And that just shows in general how this works. Notice that the 2 ended up in front of the logarithm instead of as an exponent on top of the logarithm, like with the x squared. But it's the exact same equation. I started with this 10 or log of x squared, and I ended with this 2 times log of x. Okay, that is the idea with these particular problems. I started with m to the n power. I ended with n times log b of m, base b of m. All right, that's how the power property works. That's why it works. I don't expect you to know the why. I just need you to know what it looks like. So every time I see an exponent inside of a logarithm, I want to be able to drop that exponent out in front, okay? That's the idea here. All right, so the first example today, it says, I'm gonna show you two methods for solving basic exponential equations. The first one uses the power property of logarithms, and we're gonna call it the log both sides method. All right. And so we start with this: solve 4 to the x power equals 11. So I'm starting with 4 to the x equals 11. The first thing I want to do is what I call the log both sides. And the whole idea in algebra in general, let me go on a little tangent here for a second, is whenever you're solving an equation, you have to keep the equation balanced. Keep it balanced. So if I have something like x minus 3 equals 7, I can do whatever I want to both sides of the equation. If I add 3 to the left side, I have to add 3 to the right side. And that's how I would solve this equation. Technically, I could say, let's subtract 17 from both sides. Why not? X minus 17 equals negative 7. It doesn't help me solve the equation, but I'm allowed to do it. I'm allowed to do whatever I want, as long as I do the same thing to both sides. It keeps the equation balanced. And the reason why we chose up here to add 3 to both sides is because it was an inverse operation. Addition was an inverse operation to the subtraction that it was showing. The same thing applies for exponents and logarithms. I'm in exponential form over here, 4 to the x power, so the inverse operation is actually a logarithm. And what I'm going to do is I'm going to log both sides of the equation. The equation stays balanced because I'm taking a logarithm of both sides of it. And after I take a log of both sides, I have this x power here that needs to drop out front. So the next thing I'm going to do is I'm going to apply the power property. And I can rewrite this as x times log of 4 equals log of 11. And really important to note here, the log both sides, I'm going to use log base 10 so I can put it in my calculator. So that's why I chose log base 10. You can log both sides with like a log base 17, log base 224. It doesn't matter what the base is. You can log it however you want. But the one that's going to help us is base 10. That's one where on my cell phone even, I can rotate the phone, and I've got log base 10 on my phone. All right, hopefully you have a calculator that has a log button. That's also log base 10. So that's why I want to do log base 10 for these particular problems. And I have x times log of 4 equals log of 11. The next step to get x by itself, divide both sides by log of 4. Yeah, we're allowed to divide by logarithms. And that's the idea here. Divide both sides, keep the equation balanced, by log of 4. And I'm going to end up with x equals log of 11 divided by log of 4. That is that's an exact answer. And on this particular problem, I actually asked you to round to the nearest hundredth, so 2 decimal places. So what we'll do is we'll put it in our calculator, and we'll get like 1.729, some weird thing. I can't remember exactly what it is. And then we can round it and say, well, x equals 1.73. So after we divide both sides, we're going to input in calculator. let's see, in calculator, there we go. And then the very last step, after we're done with all of that, we want to double check our answer. And the way you double check, put that answer 1.73 back in for x. And prove that 4 to the 1.73 power does indeed equal 11. And if you use the exact number that you got from your previous part, which was like I said, it's going to be 1.72 and probably like 12 numbers past it. If you put 4 to that power, you're going to get 11 equals 11. If I put 4 to the 1.73 power, because I rounded up a little bit, I'm probably going to get like 11.041 equals 11, which just means, yeah, I did it right. It's just the number's slightly off because I rounded. Okay, so the last part, check your answer. By plugging in for x into the original equation. For x. All right. That's the idea with this log both sides method. Okay. Now, so that's what log both sides looks like. Personally, I really like the log both sides method. I think I prefer it because it's algebraic to me. I like being able to see, oh, I just log both sides, that's what's going to happen. Okay. The other method you could use, we'll show you on the second problem here, is, well, actually, you know what? I'll do the log both sides method again for the second one. But the other method we could use is changing the forms. You get it isolated, and then you say, okay, let's change the forms. Like when you have 4 to the x equals 11, you could rewrite it as log base 4 of 11 equals x. That's the other way you could do it. But the problem, again, is you have log base 4 of 11. You can't put that in your calculator. So log both sides allows us to input that into the calculator. For the second example, 10 to the 3x plus 4 equals 9. Before we can log both sides, we have to isolate the logarithm. So we're going to subtract 4 from both sides, or in this case, it's the base of the exponent. Subtract 4 from both sides. And let me clarify what I meant there. We want to get this by itself on one side of the equation, and it's not by itself yet. In order for it to be by itself, I have to subtract 4 from both sides. So now I get 10 to the 3x equals 5. Now I have the exponential form like by itself, that exponential form. So now I can go ahead and do my log both sides method. And I can write this as log base 10 of 10 to the 3x power equals log of 5. I have this 3x power that can drop out front. So 3x times log base 10 of 10 equals log of 5. So that's the power property, moving that exponent out in front of the logarithm. Now, I have log base 10 of 10 here. That's kind of a nice thing because I don't need to divide by that. As long as I recognize that log base 10 of 10 equals 1. So in reality, this is just 3x equals log of 5. And then my last step, divide both sides by 3. So I end up getting x equals log of 5 over 3. And then after I divide both sides by 3, I can calculator, and I should get like x equals 0.23, again rounded to the nearest hundredth, and then check your answer. Always check. And that means just go back to the original equation. What did we start with? 10 to the 3, and then I'm going to put my answer in there, 0.23. Plus 4 equals 9. So we want to prove that this equation equals 9. And it should work. Checked. All right, when you double check your answer. And then the note I want to put down here, why couldn't we just log both sides as our first step? And that's the really important part. We need to isolate the base of the exponent on one side of the equation before we can log both sides. It gets really, really tricky if you'll get it wrong if you don't start by subtracting 4 from both sides. You got to get that base isolated before you log both sides. All right. Now, I've got 3 problems here for you guys, 1, 2, and 3. I'm going to give you guys a few minutes to work on those 3 problems. Problem 1, base is already isolated. Problem 2, base is already isolated. Problem 3, you're going to need to isolate that base. I just highlighted the base. Notice that the 4 is not part of it. Isolate that base before you before you log both sides. All right, so try these 3 problems out. We're going to go over them in a couple minutes. If you have any questions, now's your time to let me know. Okay, so looking over these 3 problems now, after a few minutes. The first one was 2 to the x equals 5. Feel like that's pretty self-explanatory. We're going to log both sides. And then we are going to apply the power property to move the exponent out in front of the logarithm. And then we divide both sides by log of 2. So the exact answer is log of 5 divided by log of 2. Put that into your calculator, you're going to get some crazy weird number. When we shorten it, it should be x equals 2.32. I'm going to find the crazy weird number real quick. So we're going to do log of 5 divided by log of 2. So we should get like 2.32192809. Something weird like that. But we're going to round it to x equals 2.32. So if you're checking your answer and you're concerned about it, check it with the big number. So 2 to the 2.32192.809. If you plug something like that into your calculator, it should give you this number equals 5. And the check should work a little better that way. So if you're not sure if you did it right or not, then that's how you can tell. It's only gonna be a real problem. Like if you got something like 4.9 equals 5, then that's pretty close. That you can probably attribute to a rounding error. In problem 2, we did notice that the number was way off, so we got to be more careful with something like that. But what you don't want to see is you don't want to see like 27 equals 5, because that is way too far off. That's way more than a rounding error. So that's what you're trying to avoid on these particular problems. Okay, let's go ahead and look at problem 2 now. 7 to the 9x power equals 15. We're going to log both sides. And then the 9x drops out in front with that power property. And now this is kind of weird because I have 9 times x times log of 7. So I'm going to need to divide twice. Essentially, what I'm doing is I'm taking log of 15 and I'm dividing by 9 times log of 7. I'm dividing by all of that. But if I don't put parentheses around this whole thing here, my calculator is going to read that wrong. And if I'm worried about my calculator reading it wrong, what I would recommend instead is doing this, or we say 9x equals log of 15 over log of 7. And then I'm going to get some weird number in there, 9x equals like 1.39. But right now I'm already starting to round, so that's going to lead to my answer being more off at the very end. So we just have to be careful with that. And then I can divide both sides by 9. So if I want to do it one step at a time, I can. And I end up getting like 0.15 here for this one. All right, that's what number 2 should look like. But again, if I can carry the whole answer through on my calculator and round at the very, very end, it's going to be a little bit closer to accurate when I'm checking the answer at the end. Okay? Any questions on the first 2 before we move to the third one? Third and final. Okay, good. Last problem. Before I log both sides, I'm going to start by adding 7 to both sides. So 4e to the 0.3x equals 20. And then 4 is not raised to an exponent, it's just hanging out. So technically this base is not isolated yet. So I have to divide both sides by 4. And that's a common mistake people make. They think the 4 is associated with the exponent, but it's really not. So you have to get rid of that 4 first before we can log both sides. All right. And I get log base e of negative 0.3x equals log of 5. And I could take this thing, using the property of exponents, drop it out in front. And then remember, e is a number, not a variable. So if I divide both sides by log of e, I get log of 5 divided by log of e. And then I'm going to get some weird number. I think in this case it was like 1.61. And then my last step, I'm going to divide both sides by negative 0.3. And I should get x equals, it's like negative 5.37. And then I can go ahead and plug it back into the equation. All right. Something else to keep in mind here, we don't have to do log base 10. Technically, when I log both sides, like we'll start with this, we're going to go back to this step right here. Add e to the negative 0.3x equals 5. I can log both sides with whatever logarithm I want. I can say, hey, let's do log base 2 of both sides. All right. But if I'm doing log base 2, I can't put that in my calculator very easily. I might have a calculator that works for it, but I definitely can't do it on my phone with a log base 2. So that's why I don't choose log base 2 as an option. All right, I could do log base 7 of both sides, log base 17, it doesn't matter. Keeping the equation balanced as long as I use the same logarithm on both sides. But one that could be useful here is if I did natural log of both sides. Anyone know why natural log might be a good choice here?
Because natural log is log base e.
Exactly. Natural log is log base e. What I'm doing is I'm trying to get these logarithms bases to match up. And what's going to happen is my 0.03x drops out in front. And now I have natural log of e, which is really just 1. So it just becomes 0.3x times 1 equals natural log of 5. I saved myself a step there because I was being smart and using the log base e. And now I can just divide both sides by negative 0.3 instead. I should get the exact same answer. It's still going to be that negative 5.37, but I did it a step faster because I used log base e. And technically, I could do that over here as well. Like, let's go back to number 1. Number 1, start with this 2 to the x equals 5. All right, look at how many, we had to do a few steps to get there. If I just did log base 2 of both sides, I'm going to get log base 2 of 2 to the x equals log base 2 of 5. I drop that x out front. I've got x times log base 2 of 2, which is really 1. And that goes away, and I'm left with just log base 2 of 5. So that works, and it saves some time. The only issue with that method is I might have a calculator that lets me put log base 2 of 5 in it. Like, I know me personally, I do not have a calculator that lets me do that. So I'm going to need to use what's called the change of base formula. And that's what this is right here. It allows me to approximate any logarithm using a calculator. And the idea is when I change base, I want to change to either base 10 or base e. Okay, so first moral of the story, when I do log both sides method, I can log with whatever base I want. All right. So now let's take a look at this right here, this change of base formula. Basically, with no numbers, just variables, it's saying if I have log base c of a, I can technically rewrite that as log base b of a over log base b of c. I can change the base to anything I want, and that'll help me put it in my calculator. In this case, I want to either have b be 10 or the number e. And that's because I can use a common logarithm or natural logarithm in my calculator pretty easily. All right, and I'll explain this more in just a second here. But basically, if we're doing log base 10, I don't need to write the base. But what we're seeing here is this base c is going to the denominator of the fraction. If I did natural log, it'd be natural log of a over natural log of c. Okay. Easy way to remember it, the base c goes to the basement, just like what we said last time. So base goes to the basement, or the denominator of the fraction. That's going to be true for these particular problems. All right, so real quick though, what change of base formula is going to do, I have this log base 2 of 5 here. I'll show you another example in a minute, but I could technically rewrite this log base 2 of 5 as log of 5 over log of 2. Look at that. Over here on the right, I already had that written down on my paper. So if I use a base 2, it's going to make it simplifying. It's going to make the simplifying part a lot easier, but I'm still going to need to change the base to put it in my calculator a lot of the time. So I can still change it to log base 5, or log base 10 of 5 divided by log base 10 of 2. I can do whatever base I want. Technically, I could rewrite this as log base 2 of 5. I can say, let's make it log base 317 of 5 over log base 317 of 2. But there's no point in doing that because it's not helping me get closer to a solution. I'm allowed to do it. It's a mathematical operation that's legal. That's fine. But it's not helping me get to my answer. So base 10 and base e, those are helping us get to the answer. That's why we want to focus on those ones specifically here. Okay, that's the idea. All right. Last thing we're going to look at today is just another example of this change of base formula. first things first, to make sure we're doing the change of base formula correctly, it's never a bad idea to guess at it. So think about it in the other form. So for example, this one I could say 3 to the question mark equals 8. Well, I know 3 to the first power equals 3. 3 squared equals 9. So question mark is somewhere between 1 and 2. Anyone have any guesses what question mark is going to be closer to? Is it going to be closer to 1 or closer to 2, you think?
2.
It's going to be closer to 2. So if we were guessing, I'd say it's going to be closer to 2. Maybe it's 1.8. Maybe question mark is 1.9. All right. But it's going to be closer to 2. And it's important to do that because when I'm changing the base, I want to make sure that 3 gets in the denominator of the fraction. If I change the base and I accidentally did log of 3 divided by log of 8, and I put that in my calculator, I'm going to get some decimal answer, like 0.0 or 0.5 or something like that, 0.4, something like that. And that is not close to 1.9 or 1.8. So that's why it's a good idea to just kind of guess at it first. And when I do the common logarithm, I put it in my calculator, I end up getting 1.89. And that seems right on with where my guess was, which is good, closer to 2. The other way I could do it, natural logarithm, natural log of 8 divided by natural log of 3. And again, this is taking log base 3 of 8 and converting it to a different form. And I've put natural log of 8 divided by natural log of 3 in my calculator. I will get the exact same number. Like every point will be the exact same. Okay, if I put it in my calculator. That's a good thing. All right, really important when we are using our calculator, we need to use parentheses. Make sure we're doing it correctly. And what I mean by that is you'll type in log of 8. It's going to open parentheses when you push the log button. You have to close those parentheses. And then divided by log of 3, you'll open those parentheses. You have to close them again. So when you're inputting in your calculator, make sure you're using parentheses and you're using them appropriately and closing them where they need to be closed. All right, 4 more problems here. I want you guys to use change of base formula and then round the nearest hundredth. All right, on these 4 problems. So we put these 4 problems into our calculator, change the base, put them in, and we should get something for the first one. I think it was like 1.29. For the second one, 1.26. For the third one, 0.67. And the last one was like 1.37. All right. So rounding the nearest hundredth, so 2 decimal places. Make sure you're paying attention to your rounding when you're doing these types of problems. All right, those are the change of base formulas to evaluate them. Any questions on those 4? Okay, great. So that sums up everything for today. I'm just going to show you the assignment real quick. Problems 9 through 14. Go ahead and cross those out. We didn't talk about that stuff yet today, so just cross those 6 out. They're not going to be due, so you only have 8 problems today. First 4 problems, use change of base formula to evaluate each logarithm. Okay. And then problems 5 through 8, solve the equation. So solving, that's what we did, solving these exponential equations. Problems 9 through 14, we haven't gotten there yet, so cross those ones out. You're only responsible for 8 problems. We have 14 minutes left in class, 8 problems. That's basically 2 minutes a problem. I would recommend you working on those right now, and you can get it turned in before you get dismissed at 1:10. And if you stay on the line, you can ask questions to me as well. We can work through a problem together. But go and work on the assignment, and we'll give you that time to work on it.